Hello and welcome to video 14 in the Different Angle 3D Blender tutorial series. This is the second part of project 2 in the series, where we're building a steel stock library, so a whole range of different models of standard steel stock sections that you can easily pull into a Blender project to construct steel fabrications using precision modelling to produce the fabrication to real world sizes. In the part 1 we looked at where you can obtain nominal dimensions and various other aspects of the different steel sections, and then we modelled 3 fairly simple hollow steel sections as a demonstration of the principles of precision modelling. In this tutorial we'll add hot rolled steel section, so it will be RSJs, channels, angles and various other readily available stock steel sections that you can obtain either locally or through the internet. And after we've modelled these different profiles using slightly different modelling techniques, we'll look at a development build of Blender 3 and show how the components that we're building in Blender 2.93 can be appended into Blender 3 and set up in Blender 3's asset browser, giving you a visual representation of each of the models and making it much visually easier to construct a steel fabrication very precisely within Blender's 3D space. We'll get on and open Blender and carry on modelling the hot rolled sections. As with the previous video, video 13, which was the first in the steel stock library project, I'm using Blender 2.93.4, which is the latest stable long-term supported version of Blender. It just gives us a bit more confidence that things won't go wrong with any of the new features that are in Blender 3. But I will open Blender 3 towards the end of the project and do a quick demonstration of how to set up the asset library, or the asset browser and the asset library system within Blender 3, ready for when it becomes stable. The rolled steel section I'm going to start with will be a simple angle iron, and we talked about where tables of steel sizes can be obtained from on the internet that aren't the expensive standards or very expensive reference tables that are in design manuals. So from those I've extracted the dimensions of a 50 by 50 angle iron section with 6mm thickness, and you'll see the toe radius is 3.5mm and the internal corner radius is 7mm. So the default screen opens with the default cube in the centre, which isn't really a useful starting point, so I'll delete that by pressing the X key and delete the cube. And in the units panel, Blender's standard setup for a new build of Blender is metric. So in the properties window, click on units. We've got metric, but at the moment it's in meters and we're working with small sizes, so we'll change that to millimeters to make it easier to input dimensions and into the text boxes, etc. So we'll press numpad 7 and add a plane object to work with by pressing Shift A for the add menu and then choosing mesh plane. In the bottom left hand corner we've now got the add plane panel, which we can open, and you'll see the size of the plane is a standard size of 2 meters, 2000mm, and we need that to be 50mm, so click in the text box and type 50 and then click outside the text box. You'll see the plane has become extremely small, so using the scroll wheel we can zoom in onto the plane. The two sides of the plane, the left and across the bottom, will now represent the outer edges of the angle iron, but the rest of the face isn't of use. But we don't have to destroy that and then rebuild edges and faces. We can modify the shape of the plane by adding vertices. So tab into edit mode and left mouse button select the top left vertex, then left mouse button select the top right vertex, and we can subdivide that edge at the top by right mouse button clicking to open the vertex context menu and choose subdivide, and you'll see another vertex has opened in the middle. Now we can use that vertex to position the inner edge of the angle iron. So to move the vertex, first of all, you could either use a bit of maths and subtract 6mm from the 25mm that the outer edges from the centre line, or we can just use modelling techniques, and one of the useful ones is vertex slide. So if you press Shift V for vertex slide, you can now drag that vertex along the top edge until it's on the outer corner. So we know that's positioned exactly on the outer edge now, 25mm away from the centre of the plane. So all we have to do is now grab that vertex, which is still selected. So we use the G key to grab it, press X to constrain the movement on the X-axis, and then 6 for the thickness of the angle iron that we're creating. And we can do the same on the right hand side. So left mouse button select the top right hand vertex, and then Shift left mouse button select the bottom right hand vertex, and right mouse button click and choose subdivide. Left mouse button select the new vertex in the centre of the right hand edge, and Shift V to open vertex slide and drag that vertex down to the bottom corner. We can now grab that vertex on the y-axis and move it 6mm to give us the vertex representing the thickness of the bottom of the angle iron. The other vertex, we can now select, left mouse button select the top right hand vertex and grab that and move it down towards the inside of where the angle will be. That's not placed precisely by just grabbing it, so what we can use now is Blender's magnet snap, and on the top bar click on the magnet icon, and then in the options to the right of that, the drop down, we'll choose vertex because we want to snap to a vertex, and we'll use the active because it's the active vertex that we want to move. So with the inner corner vertex still selected, we can grab it with the G key and constrain the movement to the X-axis, and then bring our cursor to the inner vertex on the top of the angle iron, and it'll snap level with that vertex. And we can do the same on the y-axis. So with the vertex still selected, grab it with the G key, constrain it with the y-axis, and just bring the mouse over the top right hand vertex, which represents the inner edge along the bottom. And we've now got that positioned exactly on the inner corner. So all the vertices that we've got are now positioned correctly. What we now need to do is add the fillet radiuses on the corners, or the toes of the angle iron. So we'll select the inner top vertex and shift select the inner right hand vertex, and we can then use Control B to open the bevel menu. Just drag the cursor slightly, you'll see the selected vertices are no longer selected, and then left mouse button click to accept them. These vertices don't do anything because it's set, the bevel panel is set for edges. So if we change it to vertices, you'll see a chamfer form on the top edge. We want to have a radius, so we need to add some segments. So we'll add the segments, and we'll make those segments up to 5 for the toe radius, and we'll make the toe radius, which is shown as width of the bevel, as 3.5 millimeters, 3.5 in that text box within the bevel panel. That gives us the outer radius corners. We can now do the inner corner. by left mouse button selecting the inner corner and repeating the process of Control B for bevel, move the mouse slightly, and in the bevel panel we'll change the width of the bevel, this time to 7 for 7mm, and it's a vertex bevel again, so we select vertices as the vertex bevel, and this time just increase the count of vertices because there'll be some faceting because they're quite spread out if we leave them as they are, so we'll change it from 5 to 9 just to give us a nice smoother inner bevel. You can have these lower poly and use less, and the shading menu should get rid of most of the shading artifacts, but for dimensional accuracy, the closer the vertices are on radiuses, the more accurate the radius is on screen. So we've now got the shape of the angle iron, so we can just zoom out a little and move around into a more 3D view. This represents the bottom of the angle iron, and as we've done in the first video, we'll just extrude this because it's already got a face, it knows which way the face normals are, so we can extrude this 300mm. So select all by pressing the A key and all the vertices will be selected, and then press E to extrude and 300 as the length we're extruding, and enter. If you just zoom out a little bit more, you'll see we've now got the angle iron profile made, so we can tab back into object mode, and in the outliner at the moment it's called a plane, so if we double click on where it says plane, we can now change that to 6 for the thickness of the angle iron, X for by 50 by 50, and we'll just call this equal angle. I've got capital X pressed, so do it again, equal angle. Just change the X's as well to lowercase to make the numbers easier to read. So we've named our first roll steel angle. We can now move the angle iron out of the way, and we'll move it with the G key to grab it on the X axis, so X to constrain it to the X axis. We'll move it -1 metre on the grid, so it's -1000 as we're in millimetre units. That allows us now to do the next profile, and the next one I'm doing is the fairly simple one again, a parallel flange channel. Very similar to the angle iron, but with different thicknesses for the web and the flange, and the top flange that you haven't got on the angle iron. So we'll go into numpad 7 for top view, and then Shift A to add a mesh plane. And in the add plane panel we'll change the 2000mm of the plane down to 150, which is the largest dimension of the channel. We're doing 150 by 75mm. Now to get the 75mm, which is half the 150mm of the plane, what we can do is tab into edit mode, and with all 4 vertices selected we can scale on the x-axis 0.5, because 75 is half of 150, it will scale it so the top dimension is 75mm. And just to confirm that, the edge length, we're now at 75mm, and take that out of view again because it complicates things. The profile is very simple, 10mm flanges, and to describe the channel shape without the fillet radiuses in the corners, we need 4 more vertices on the right hand edge. So to do this, left mouse button, select the bottom right vertex, and then shift left mouse button, select the top right vertex, and then right click the mouse to bring up the vertex context menu and click subdivide. And in the subdivide panel we'll change the number of cuts to 4. So we now have 4 more vertices on the right hand edge. Select the second from top vertex, and using the same principles that we did with the angle iron, press Shift V to open the vertex slide and drag the vertex up to the very top of the plane. We can now move that the 10mm of the flange thickness. So we'll again grab that vertex while it's selected on the y-axis and we'll move it minus 10mm. And do the same for the second from bottom vertex. Left mouse button, select the vertex. Shift V for vertex slide and drag it to the bottom. Then G to grab the vertex on the y-axis and move that one a positive 10mm on the numpad. So number 10 on the numpad, and enter. So we've got the points where the inner flanges will come to the outer edge of the channel. Select the 2 other vertices, and we can move these now. We've got magnet snap selected, and it's selected for vertex and active. So we can move these on the x-axis to the back edge. So we'll grab the 2 vertices on the g-axis. So we'll grab the 2 vertices on the x-axis and snap them to the back edge. The thickness of the web is 5.5mm, so we'll grab them again on the x-axis and 5.5 on the keyboard, and then enter. So all we have to do now is select each of them individually, and with the magnet snap them up to the inner vertex of the flange. So we'll grab the top of the 2 web vertices. So select the top of the 2 web vertices, grab it on the y axis and just move the mouse up to the vertex that represents the thickness of the top flange. And snap there, and then left mouse button, select the bottom web vertex, grab it on the y axis down to the bottom inner flange vertex. And that's give us the thicknesses, so all that's left to do on this one is to add the 2 12mm inner corner radiuses. So select the 2 vertices with the left mouse button, shift left mouse button, and then shift B to bring up the bevel menu and move the mouse slightly, and then enter. That didn't work. Try again. It was not shift B, sorry, it's control B. Drag the mouse slightly and enter to bring up the bevel panel. We're beveling vertices again rather than edges, and we want to bevel the vertices 12mm. So in the width panel, enter 12. And the segments, again, I'm going to put 7 segments to keep the vertices fairly close together to describe a fairly accurate arc in the corner. And that's the profile, very simple to do. And we can now select all and extrude it. And because the face is already in there, it'll extrude along the normal 300mm. And enter. And tab back into object mode, and we've now got the channel. For this one, we can go into the object and shade smooth, and you'll see the shading artifacts because we haven't got auto smooth activated. So if we tab back in to edit mode, select all with the A key, and then in the object data properties we want normals and auto smooth, and that smoothed everything. So if we tab back into object mode we get the correct shading. We didn't do that previously on the angle, so I'll just select the angle, click auto smooth, and in object go to shade smooth. So both of them are shaded smooth again. So with the angle line selected, if we shift select the channel to get both of them, we can move both of them out of the way a meter. So again, we'll grab the two objects on the x-axis and move them -1000 millimeters. Just select the channel again, and in the outliner the channel's named as a plane, so we'll double click on that and change it to 150 times 75 parallel channel. The next profile is a little bit more complicated. We'll look at the taper flange channel on 152 by 76 as the measurements. This is a leftover from the old imperial channels, so you've got sort of points of a millimetre. Things aren't quite as straightforward as with the more modern channels. And what makes it more complex is the taper that we have on the flanges. That can cause problems of moving vertices, and we just need to be aware of that, so we have to use different modelling techniques to get this profile. So I'll start off again by adding a plane, which is Shift A for the add menu, mesh and plane. Because I've turned Blender off and on again between the previous channel section, it's coming at 2 meters rather than 150. But we need to change that now to 152.4 as the biggest dimension of the channel, and then we can go into numpad 7 to go to top view and scroll wheel in to look a little bit closer. The 76.2 width of the channel is half of the 152.4, so again we can tab into edit mode, and with all the vertices selected we can scale the x-axis by 0.5, so it's S for scale, X for the axis, and 0.5 as a scale factor, and that gives us a 76.2 across the top and 152.4 as the height of the channel. The problem we've got now is with those tapered flanges, we don't know where the end flange needs to be, but we do know where the web thickness is, and we know the flange thickness in the centre of the short length, the inner length of the flange, is midpoint. So we can start off as we did with the other channel by just subdividing the right hand side. Select the two vertices of the right hand edge of the plane, right mouse button click, subdivide, and then change the number of cuts to 4. And again we can select the second to top vertex on the right hand side and use the vertex slide, Shift V, to slide it up to the top, and then grab the vertex and move it on the y-axis -9 millimeters for the mean thickness at the centre of the flange, and do the same at the bottom. So we can edge vertex slide, Shift V, the vertex to the bottom, and then grab it on the y-axis 9 millimeters. And then the middle two vertices again can be moved into the back, so we can grab those on the x-axis, and with magnet snap still enabled, just snap it to the left hand edge by taking the mouse over one of the vertices on the left hand edge, and then we can move it the 6.4 millimeters back the width of the web. So again, G for grab, X for the axis, and 6.4 is the dimension. And finally, or almost finally, take the top vertex of the two we've moved for the inner side of the web, grab it on the y-axis and move it up to the inner 9 millimeter vertex of the flange, and then do the same for the bottom one. Select the bottom of the inner web vertex, grab it on the y-axis and move it to the bottom inner flange vertex. Now the problem we've got if we rotate these two flanges 5 degrees is it moves, because it's rotating it, it's moving the two inner and outer vertex out of position, so they're no longer parallel with where the back web should be or where the toe of the channel is. So we need to now separate the two edges so we can move them separate from the web and the filler edges that fill the front of the flanges. So select all and then press X for delete, and we choose only faces, so we only take the faces out of the middle. We now need to delete the back edge, but first of all, before we delete that, we need a reference point to know where that back edge should be. So select the two vertices of the top edge and subdivide it. Right click on the mouse and choose subdivide, and then select that middle vertex that we've just created and vertex slide it to the left. So we don't need to do that, we can just vertex slide it to the left and snap it onto the vertex that represents the top of the inner web. So that gives us a reference of where the inner web should be, and we can now delete the edge that represents the inner web. So select the two vertices of that edge and X for delete, and this time edges to remove that, and then select the 4 right hand vertices of the profile, and again press X to delete the edges and choose edges from the drop down menu. So we've got the two inner edges with the width at 9mm, which is the correct width for the midpoint of that edge. So what we can do now is rotate those 5 degrees. So select the bottom edge by selecting and shift selecting the two vertices, and then press R for rotate and 5 for the 5 degrees of taper, and do the same on the top one. So select the two vertices of the top inner flange edge, press R for rotate, and this time -5 to give it its rotation. So the problem we've had now we've rotated them is if we just bring down an edge from the reference vertex we put on the top edge. So we'll select that top vertex and press E for extrude and bring an edge down on the y-axis, so Y for the y-axis, past the angled edge of the bottom flange, and then zoom in. You'll see that the angled edge has been rotated out of position with regards to the web, or what will be the web. So we need to be able to extend this edge that's angled to form the inner face of the channel's flange. Now to move that, if we put the move widget on and just select one vertex, you'll see the global orientation doesn't line up with the edge anymore, and if we look at the other orientation options, the local one doesn't, the normal one doesn't, and the gimbal one doesn't. So none of those are really any use to drag that edge back to where it should be and maintain the 5 degree angle. So what we have to do is set a custom orientation, and to do that we can use the edge as the custom orientation. So if we select both vertices of the bottom edge that's at 5 degrees, and in the orientation drop down we press the plus arrow, or the little plus that's on the right of the options, it adds a new orientation, and this time it's added the orientation as an edge. And what we can do now is select the end vertex, and in the magnet snap change from vertex to edge, so we're now snapping on two edges, and with the green handle, or lime green handle of the move widget, if we click on that and move it until the cursor is close to the edge, it'll snap the vertex onto that back edge, and we can do the same at the other end. What we first need to do is go back into global orientation, extrude the bottom right hand vertex. So again, extrude on the y-axis past the tapered edge, and then we can select the tapered edge, go back into the edge orientation that we've set up, the custom edge orientation, and again with the yellow or lime green indicator we can click on that and then move the mouse over the new edge that we've just done perpendicular to the bottom of the channel. So that puts that vertex in the right place. So now we can just snap the end vertex that fills between the two and grab it and snap it onto the end of the angled edge, and that puts it in the right place. And do the same the other end, snap the vertex at the bottom of the edge that we're using for the inside of the web, and just grab it and snap it onto the end of the tapered 5-degree tapered edge, and that puts that in the correct position. So we could do the same on this edge now. Again, we select the top tapered edge, but even in edge taper it's the opposite angle to what we've set the orientation up. So we can go into edge where it's and delete what we've got at the moment as the edge transformation or the edge orientation. Set up another new orientation which will be called edge, representative of that one. This time it's in the correct orientation again. So we can select the end vertex. If we zoom right in on that, you'll see the difference of the move. And then we can grab the yellow indicator on the move widget, grabbing it, taking the mouse over the back edge for the inner part of the web, and it snaps it into the right position. And on the other end, we can again select the top right hand vertex, change the orientation back to global orientation, and extrude it on the y-axis. So try again, didn't extrude that time. Extrude it, so the E key on the y-axis down past the tapered edge. So we can go back to the tapered edge now, go back into the edge orientation, and again with the green move widget handle we can bring that vertex onto what will be the joining piece on the open end of the channel. So that puts it in the right position. Then grab the vertex that we've extruded down to form the front face of the flange, and then grab it and drop it back onto the end of the tapered edge. Finally, to get the inner corner joined, we need to first of all select the back edge of the web, which runs all the way to the top of the channel, and subdivide that to make a new vertex. So right click and subdivide, and then the new vertex we can grab and snap onto the end of the tapered edge, and then select that and the top vertex of that edge that we no longer need, and then click X to delete it, and click edges to delete it, and then select the vertex that we don't need on the very top edge, and again click X to delete, and this time we'll dissolve the vertex to get rid of that. So we've now got a clean profile of the tapered shapes. So if we select all, because some of the vertices aren't joined, they'll be doubled over the top, so we need to merge those, and we press M for the merge menu and merge by distance, and you'll see 4 vertices have been removed, and that represents the 4 doubled vertices that were on the ends of the tapered flange. While they're all selected after you've deleted the merged or the doubled vertices, we can just add a face to form a face on the inside. So the final thing to do will be to add the bevels, and if you select, first of all go back into global orientation, and we'll take the move widget off by just clicking the select box. We can select the two vertices of the inner web wall and press Ctrl B and drag the mouse slightly to open the bevel panel. And we're vertex beveling, and the bevel needs to be 12.2 millimeters in the width panel, so 12.2 in there, and again we'll segment it 7 times, so you've got 8 segments, 7 new vertices on the inner bevel, and then select the 2 vertices representing the inner flange on the right hand side of the flange, and we can bevel those 2.4 millimeters. So again, with them both selected, press Ctrl B for bevel, drag the mouse slightly, select vertices bevels, and change the width to 2.4. There's far too many vertices for something as small as that to be necessary, so we can change that from 8 and bring it down to 3 to describe the front radius. And that gives us the profile then of a tapered flange channel. A lot more difficult than just keeping things square as you do with the more modern sections. If we just rotate it round to a 3D view, select all, we can extrude that 300 millimeters. I'll undo that, Ctrl Z, because the normal at the moment is pointing down on the face we've just added. So if we extrude it -300, it will follow the profile of the other ones we've created. But at the moment, that's indicated that the normals are pointing inside rather than outside. So we need to select all and then press Shift N to recalculate the normals. If we now tab into object mode and select the object menu at the top bar, and we'll go shade smooth to shade it, and because we haven't got auto smooth selected, the shading's gone weird because it's trying to smooth off all the top edges, so we can then click the auto smooth in the properties panel under the normals tab. And that's the taper flange completed. So in the outliner, double click on plane, which is the object we use to make the taper flange, and we'll change its name to 152 by 76 taper flange, taper channel. Taper channel, and enter, and that completes that one. So we'll select the other 2 components and move those all a metre across so we can work on the next profile. So with the 3 components selected, press G for grab, X for the x-axis, and -1000. G, X, -1000 to move them out of the way. The final profile I'll look at is again another fairly simple one, and that's a universal beam. It's just to show that you can model around a centre line using the mirror modifier, but it's very similar to the parallel flange channel. If you was doing an RSJ, the old-fashioned type beams with tapered flanges, then you'd need to follow the tapered channel method to get the profile on one side. So again, we'll start by adding a plane. So Shift A, add mesh plane. Because I haven't come out of Blender between the previous channel and this, it's put it in at the same size as the previous channel at 152mm. So we need to change the size to 254. 254. And that gives us the height of the universal beam. I'm going to go into numpad 7 for top view and scroll in again. Because the width has no representation to the height, we can't just scale it easily. So a very easy way to create that is to tab into edit mode, press Ctrl R to cut an edge loop, and cut a vertical edge loop across the plane, and then press escape to leave it in place and enter to make sure it's cutting through the plane. We can now delete all the 4 corner vertices, just leaving that one edge. So X for delete once the 4 corner vertices are selected, and delete vertices. So we just have now one edge running directly over the Y axis. The width of the universal beam is 101.6, so we need to extrude this on the X axis, half of that, which is 50.8. So with the 2 vertices selected, press E for extrude, and because we aren't extruding a face, it doesn't know what direction to extrude in, so we'll constrain it to the X axis and then move it a distance by typing on the keyboard 50.8, so 50.8, and that gives us half of the profile of the universal beam. We can now add a mirror modifier, and so we go into the modifiers tab on the properties panel, add modifier, and go down to mirror, and it automatically mirrors across the X-axis, so whatever we model now on this side will be repeated on the other side. You can change the axis by changing some of the aspects within the mirror modifier panel, but for this we don't need to. So as with the parallel channel, we need 4 vertices on the right hand edge. Select the 2 vertices of the right hand edge, then right mouse button click subdivide, and in the subdivide panel increase it to 4, and select the second from top vertex, shift V for vertex slide and slide it to the top, and then G to grab the vertex on the Y axis, so Y for the Y axis, and move it -6.8. So that sets the width for the top flange, and on the second from bottom vertex on the right hand edge, select it, shift V for vertex slide, slide it to the bottom, grab with the G key on the Y axis with the Y key, and 6.8 for the width because it's moved in the positive direction. And then the 2 inner vertices, select them both, grab them on the X-axis, the X key for the X-axis, and we need to snap them to the inner centermost edge to put them on the center line, and then half of the thickness of the web, which is 2.85. The web's 5.7, so grab the 2 vertices on the X-axis, 2.85. That gives us the thickness across the web. Then select the top vertex on the inner web, and we need to change the magnet snap back to snap into a vertex, and we can then grab that, so G for grab, on the Y axis, and then go to the inner vertex on the top flange, and do the same for the bottom. So select the bottom inner web vertex, grab it on the Y axis and move the cursor over the inner flange vertex at the bottom. And that gives us the basic profile. So all that's left to do now is bevel the 2 inner vertices on the web. So select them both, and then Control B for bevel, drag the mouse a little bit and click to open the bevel panel, select vertices because we're doing a vertices bevel, and the width of the width of the radius, or the width of the bevel, which is the radius, is 7.6. So change the width to 7.6 and enter. And again, if we zoom in, we can just change the segments from 3 to 5 for that, and that's repeated on the other side. Now, to make that a single item, we need to apply the mirror modifier rather than having it with the modifier being used. So tab back into object mode, and in the modifier panel, on the modifier's top bar, click the down arrow just next to the camera and click apply, and then tab back into edit mode. So we've got the profile of the RSJ, but we've got an unnecessary edge running through the middle of it. So select the 2 vertices of the edge and then press X and delete. This time we'll dissolve the edge, and that takes away the edge and the 2 vertices that are no longer needed, leaving just the face of the of the universal beam. So if we zoom out a bit and in the 3D view, select all and extrude 300. And again, it's gone in the opposite direction, so Control Z to undo that, and we'll go, while everything's still selected, go extrude and minus 300. But as I've said, that indicates that the normals are pointing in the wrong direction for the enclosed space. So select all and Shift N to recalculate the normals. And that creates the universal beam section. We'll go into the object data properties and click on Auto Smooth, and in the menu in edit mode for faces, we'll click on faces and select shade smooth and tab into edit mode, and that's the universal beam. So we'll put this in to the outliner, so double click on plane and change it to 254 by 102 and by 22. The 22 designates the weight per metre of the beam, but you can have several beams of the 254 by 102, but different thicknesses to give them different strengths. So that needs to be added to the designation for these, and that's a universal beam. Enter. So that again gives us the basics of the different steel profiles and how we can use different techniques to model them very precisely to real world sizes. In video 1 we set up the collections for the different profiles. I'm not going to do that in this. What I'll do is just append them across into an asset library I've built for myself into Blender 3. I've been over to the Blender website and downloaded the daily build of Blender 3. This is alpha software, so it's inherently unstable and it's not recommended for production use. If you're uncomfortable going into hidden config files, if there is a crash that can't be resolved, then don't download it, don't use it. Leave it to the others who are experimenting and working on getting Blender up to a stable standard. But if you do want to have a go and you feel confident at your own risk that you want to have a play with Blender 3, I covered downloading and installing Blender in video 2 of the Getting Started section of the Different Angle 3D channel on YouTube. There's just one or two little differences. So if you go to blender.org and click on the top download link in the top menu of the website, it'll take you to the download page, and if you scroll down the download page you'll come to a section called Go Experimental, and click on the Download Blender Experimental button on that section, and it takes you to some options for the experimental builds that are currently available for testing purposes only, for mainly experienced people that are fairly comfortable in rebuilding their software trees and what have you if something goes critically wrong. And we're looking at Blender 3, so it's the third one in the list that you need to click on and download, and then it's just following the procedures that are in video 2 of the Getting Started section to load the Blender 3 software. So this is the clean daily build of Blender 3 that I've downloaded. There may be differences when you download one because it is changing on a daily basis, but the interface is very, very similar to Blender 2.93, so you shouldn't have any problems finding your way around if you've already been using Blender 2.93. We're here to talk about the asset browser and just give a demonstration of what's coming when Blender 3 is released and how we can use that for a much more efficient way of bringing items in visually into the 3D view. So I've just dragged up the timeline to make a little bit more area, and we'll turn the timeline into the asset browser window. So in the editor type button, we'll click on that and you'll see there's a new, under data there's a new window which is the asset browser, which opens the asset browser. You've got the tool panel on the left and you've got the settings panel on the right. Still toggles with the N and the T key as it does in the 3D window, but we've got no assets in there at the moment. So what I'll do is delete the cube. So select the cube and X to delete it. So there's nothing in the scene other than the light and the camera. And we'll append in some steel assets from a library I've been building of my own. So as we've done in the previous one, to append, you click on File and then go down to Append, click on that, and the file browser window will open. So navigate to where your assets are that you've been building in anticipation of Blender 3, and we can choose the file that I've used with the assets in for this demonstration, but it'll be your file wherever you load it. And we want to bring in the collections, so click on collections and then bring all of the steel collections that have the steel profiles and append them into Blender 3. So straight away we've got everything in Blender 3, but at the moment they're just objects. They're not part of the asset system, so we need to turn them into assets, and to do that in the outliner we can select. So I'll start off with the box section, select the box section and right click on it. This is an experimental build, so it might not work at this stage, and you go down and you'll either have a load asset or under ID data, or make asset rather than load asset, but in this it's not available because it's still experimental. So what we need to do is enable the experimental features. We go into the edit preferences, and in the preferences window under interface we've got an option called Developer Extra. So if we click that, it will then bring up the experimental button on the left and navigation of the preferences window. So click on experimental, and then in extended asset browser is the option that we need to enable. So we can then close the preferences window. Now if we right click in the outliner and go down, you've got a new option which is mark as asset. So click mark as asset and it will bring all those items in. So that's brought in all of the box section. It's created general images for the different assets, but they're not very visual, so we'll look at how we can change that in a minute. But I'll bring in all of the assets that I've brought over from my collection. Mark as asset for that one. So all of the circular hollow sections comes in, and the same for the rectangular section, Marcus asset. And equal angle, so I'll just work through these very quickly. So you'll see all the items get marked now with a new icon to show that it's part of an asset library, and we've got them all within the asset browser window. Not very easy, well organised, but what I didn't do is bring them into the asset with the collection, because if you just bring the collection into a project, you bring all of the assets that are under that collection, and some of them are quite big lists of like the rectangular and square box section are quite big lists that you have to bring them all in. You may only want one section from it. So that's how you create the assets. If we open, I'll click on the largest of the tubes, 5 by 168.3 diameter tube. And if we go into the settings on the right, you'll see there's a preview of it. It's not got a material assigned to it that's come across correctly, where some of these RSJs have, but the material should show. Let me just give it a chance under this mode. So the materials have come across, but it's not been picked up by the asset browser exactly as you would expect, but it is a development build, so there will be glitches at this stage, but it gives you an option as well to rebuild the preview. What I'm going to do is just swap the material on that and change it to what the material I used for the steel black, and it'll come across, and you can then refresh. If it understands the material you're using, it will refresh. So there's something in the material I built for the round tube slightly different to the rest of the materials, but that's the crux of getting them into your asset library. You can also take your own screenshots or renders of each of the components and bring them in through the file browser. I'm not going to do that, but it's something that you can do when Blender 3 becomes more stable. If you're building a complex asset library, you can have much better thumbnails than the standard that gets imported in. The last thing to do is to save the asset browser, and the Blender website gives you locations of where the default browser would normally be located. You can find more information about where to save on the wiki.blender.org, and there's some development manuals being built there, and it gives the file paths for Windows, Linux and Mac operating system in there. I'm going to use the standard location, and if we click on the preferences window again, under file paths there's a new area called asset library. It gives the default as home, or as home, your location, documents, Blender, assets. I'm using Linux, it's different slightly in Windows. And from there we can now save the file. So just file, save as, and go to documents, Blender, assets, and save it as steel stock library. So that now becomes available as a default library because it's saved within the asset section of the default area. So we can close that now. So File, or open a new document as a general rather than closing and starting again, because that's saved. And again, we can delete the cube and change the timeline into the asset browser. At this time, we can now set up the asset browser to go to the default area, and straight away it's found the file with all of the components in. So if we want to use those components, we can now just drag them and drop them within the 3D view. And this is early stages yet, but when you're building fabrications with a number of different steel sections, it's very quick and easy to bring them into view. If you want to refine what you're looking for, if you're looking for box section steel, you can just use the filter function under search and type in box, and that narrows it down to just the steel type. I think that shows that Blender's asset browser that's being developed is going to be a real asset for Blender, not just for storing libraries of parts. It will revolutionise the way models can be built from existing meshes that you've built into a library if you think they'll be useful in the future. I know I've spent countless hours looking over past blend files knowing I've modelled something, but trying to find the location of where it is so I can append it into a new project isn't always a fast and easy thing. So this will be a great feature in the forthcoming Blender 3. The precision modelling part of it is a little trickier than just pushing vertices around as you would normally mesh model. But again, it's a skill that's well worth learning. It does give you the opportunity to be able to create accurate mesh models for printing or taking drawings off so you can actually produce them in a home workshop. I don't think it's efficient enough to compete with any of the CAD packages out there, but it does give the home user something that once you become familiar with can be a very efficient way of building assemblies together to make sure projects you're doing at home actually work. Thanks for watching to this stage. The next project will be to use the assets that we're creating of the steel stock library and build a manual plasma cutting table for cutting up steel. It'll be the first of the real practical build projects and design projects in terms of home engineering. Thanks for watching, and don't forget to subscribe if you've enjoyed this, and it'll keep me motivated if you do. Thanks again. See you soon.